We're going to take a look at a new numbering system. They're called complex numbers. They involve what are called imaginary numbers. Now, to introduce this system, I'd like to give you a little background on the number systems that you're familiar with. So, looking back to the number systems that you're very familiar with, you started out when you did number systems, you looked at natural numbers. Natural numbers were the numbers that you could just count. For instance, 1, 2, 3, etc. So that was the first numbering system you were introduced to. And the only addition we had on that very quickly was we added the number 0 to it, which made the whole numbers. So that's 0, 1, 2, and 3, and etc., all the way up. Then negative numbers were introduced to the counting numbers, so all of their opposites, and we called those integers. So it's like all the way up to -5, -4, -3, -2, -1, 0, 1, etc. And just keep going. So those are called integers. Then you were introduced to the numbering system that included fractions. Those fractions were called rational numbers. It has the word ratio in it to represent the idea that these can be written as a ratio of two integers, like 2/3 or 3/5, those kind of numbers. If we write them as a decimal, they're a decimal that repeats or ends or terminates. So you had like 2/3 is 0.6 repeating. 3/5 is 0.6 and it stops. So repeating or terminating decimals, those are included in rational numbers. We then also talked about, you came up with, after that, irrational numbers. Now, irrational numbers were the ones that had, for instance, you were introduced to pi when you started talking about geometry concepts. And these are decimals that never end and never repeat. Also, which is critical to this lesson, is you were introduced to square roots that didn't come out or simplify out of the square root, like the square root of 5. That doesn't come out of the square root, and if you look at its decimal, it never ends and never repeats. So if we had 4 square roots of 7, for instance, never ends, never repeats. Those are irrational numbers. If we put rational numbers and irrational numbers together as one set, we call those real numbers. Now, we are ready to introduce a new system that includes numbers outside of the real numbers. And it's based on this idea of square roots. Notice these square roots, we always had square roots of 0 or positive numbers. We're ready to introduce, what if we have the square root of a negative? So these numbers, like if you had the square root of -16, for instance, you know what the square root of 16 is? It's 4. But what about -16? We call these imaginary numbers. And for instance, we're going to find a notation where we can take the square root of -16 and we're going to make it 4i. So when you have a negative square root, we'll introduce the imaginary unit I to take care of representing that. When you put imaginary numbers and real numbers together, you get what are called complex numbers. And that's the topic. We're going to do an introduction to complex numbers. They're in the form of a plus bi, where a and b are usually integers, and I represents the imaginary unit that helps us take care of working with the square roots of negatives. Now, let's do some background on this as well. So first of all, a little bit about radicals. We have square roots, cube roots, all those sorts of things. We're going to talk about roots for a moment. And if we have the square root of a number, let's say a here, okay, this number here is called the radicand. Okay, this is called the radical symbol. Now, for instance, when we look at this, you want to make sure you deal with the radicals correctly. So something under the radical does not interact with the numbers outside of the radicals unless we can simplify them. So we're going to look a lot at simplifying radicals. So just as a reminder, if you have something like the square root of 50, that's going to be the square root of 25 times the square root of 2, which is going to be 5 square roots of 2. That's it simplified. If I have the square root of, if I have 5 square roots of 2, and I want to add to it, let's say 10 square roots of 2, I can add those two and get 15 square roots of 2. That's simplifying radicals. If they don't have the same radicand, you can't combine them. So if I had, for instance, 5 square roots of 2, and I was trying to add to it the square root of 7, you can't simplify that because these are different radicands. They're not like terms. They can't be added together or simplified. So that's what we're going to be looking at is working with those kind of numbers in the real numbers, but we're going to add to it now negative radicands. So the key to this is that imaginary unit. So the imaginary unit, I'll add this down here. Our imaginary unit here is going to be the square root of -1 is going to equal I. So we're going to use that idea because what we'll do is take this and apply it to working with negative radicals. So simplifying negative radicands, if for instance you have the square root of -9, okay, there's a negative inside of that. We can't do a square root of a -9 unless we separate it, and we're going to make it the square root of -1 times the square root of 9. Once we take that square root of -1 out, we can do the square root of 9, that's just equal to a 3 times the square root of -1. What are we going to do with that square root of -1? Up to this point, until we've introduced imaginary numbers, we haven't been able to work with it. So this idea, the square root of -1 is equal to I, this means that this is just going to equal 3I. So let's do another example. Simplifying these, if we got the square root of -75. So you take out the square root of -1. So in this idea, you're going to take this I out, the square root of the negative. 75 we can separate into the square root of 25 times the square root of 3. That's because I know what the square root of 25 is. So I'm going to make this a 5 and this an I. So I'm going to have a 5I. The square root of 3 can't come out, so it stays the square root of 3. And so I just end up with 5I times the square root of 3. Okay, it's probably best to typically put the I at the end. So we're going to make this 5 square roots of 3 times I. Just remember, when you write it like this, make sure that radicand ends with the 3, that radical symbol ends with the radicand of 3, and you do not put it over the I. All right, last one, let's try doing the square root of -64 times the square root of 28. All right, we're going to make this one into the square root of -1 times the square root of 64. We know the square root of 64. Square root of 28, what perfect square goes into 28? Well, 28 is 4 times 7. 4 is a perfect square, so I'm going to make it into a radical times the square root of 7, which I can't get out. Square root of 64 is equal to 8. Square root of 4 is equal to 2. Square root of 7, I can't do anything with it because it's not a perfect square, so it stays trapped under the radical. But then the square root of negative 1, I make into an I. So I get 16 square roots of 7, I as my answer. So simplifying with negative radicals, radicands, you can take that I out and then simplify the radicals after that. All right, so this imaginary unit, we're going to work with it now in simplifying imaginary numbers. So it's critical to recognize that this allows us to do the square root of negatives. So these are our key laws or rules here. Square root of negative 1 equals I is 1. We've got I squared. If you square both sides here, you get I squared equal to negative 1. So these are two that we're going to use quite a bit. If you have the square root of a negative, you use I. If you have I squared, it's going to equal negative 1. Because squaring both sides here, you get an I squared, square this one, and the square of a square root gets rid of the square root, just gives us the radicand. Now this is also going to turn into a pattern. The pattern will be, if I build on this one here, and just build on this and make a chart here for us. Okay, this chart is going to be the square root of negative 1 equals I squared is equal to negative 1, I cubed are these two multiplied together. I times I squared is I cubed, so negative 1 times I is negative I. And then I to the fourth is going to be the same as I squared times I squared. Well, what's negative 1 times negative 1? It's equal to positive 1. So this becomes a repeating pattern that we're going to have this cycle through. Because what is I to the fifth? Well, I to the fifth is the same as I to the fourth times I. What's I to the fourth equal to? It's just equal to 1, so I just get I as a result. What's I to the sixth? Well, that's the same thing as having I. Notice I'm going to just take it and separate into these. It's the same as having I to the fourth times I squared. Well, I to the fourth is equal to 1. I squared is equal to negative 1, so it equals negative 1. I to the seventh is the same thing as I to the fourth times I to the third. Why do I keep focusing on I to the fourth? Because that's equal to 1. I to the third is equal to negative I, so it's equal to negative I. And I to the eighth is equal to I to the fourth times I to the fourth. Both of those are equal to 1, so that just equals 1. The pattern keeps repeating where every fourth one becomes the one that's equivalent in this chart. So what you want to do is, let me do a couple examples here, is if I think of these in terms of rules of exponents, let's say I want to simplify I to the 23rd power. Well, think of it this way. If I have I to the 20th power times I to the third, I to the 20th power is the same thing as I to the fourth to the fifth power, just separating it out, times I to the third. What is I to the fourth equal to? It's equal to 1. 1 to the fifth power is just equal to 1. This is the same thing as I to the third, which we can simplify down to the opposite of I. So you should be able to, whenever you have I to a power, you should be able to have it come up with one of these four answers. Let's try another one. What is I to the 4001 power? Well, again, I really want to focus on that I to the fourth power because that is equal to 1. So what I'm going to do is separate this out and make this I to the 4000. Why 4000? Because 4 goes into it, times I to the first. I to the 4000 is the same as I to the fourth to the 1000 power, times I to the first. And now this is just 1 to the 1000th power, which is just 1. equals I as an answer, which is one of these answers. All right, and we'll do one last one here. What if we have 5 I to the 20th times 3 I to the 5th? Let's simplify this one. All right, so we're going to multiply the numbers. So when you multiply, you can multiply the 5 and the 3 together. That's the commutative property of moving those two together. That's equal to 15. When we multiply these two, when you multiply two things with the same base, you add their exponents. So it's going to be 20 plus 5, which equals 15I to the 25th power. Now let's do our magic with this pattern. I want to look for a factor of 4. So I'm going to do I to the 24th, because 4 goes into 24, times I to the 1st, which is in order to get the 25th power. What is I to the 24th? Well, that's the same thing as I to the 4th to the 6th power times I. Well, I to the 4th is equal to 1. So 1 to the 6th power is just 1. So we have 15 times I for a final answer for that. So this is simplifying imaginary numbers. We're working with these, all right? Now, if you were instead working with complex numbers, so complex numbers adds a real part to it. So just so we look at that, a complex number, this was on the previous page, I'll just restate it here. A complex number is in the form of A plus BI, where A is the real part, and BI is the imaginary part. So what we want to do is we want to take, for instance, a number like 2 plus 7I. This 2 is the real part, and this 7I is the imaginary part. So it looks like a binomial, like we've just been dealing with in our chapter on quadratics. This looks like a binomial, and it operates a lot like a binomial. The key to doing these problems that I'm about to do is to use similar terms. That is critical for doing these problems. So when I take, for instance, I'm going to take 4 plus 3I, that's a complex number, and I'm going to add to it 9 minus 2I. Now, what we look at, these are two complex numbers, real part imaginary, real part imaginary. When you look at these, you're going to combine the real parts and then combine the imaginary parts, which is not too difficult. So I'm going to combine the 4 plus the 9, that gives me 13, and the 3I plus a negative 2I is just going to be plus 1I, so plus I. So really, if you look at similar terms like you've done before with variables, I is a letter, it's not a variable. Remember, it is the imaginary unit, it's the imaginary constant, but it is not a variable, but it operates a lot like variables when we do our mathematics with it. Now, what if instead we're going to multiply these together? So let's say we have 2 minus 5I times 7 minus 3I. So we multiply these a lot like what we do when we do our binomials. When we multiply them, we're going to double distribute. 2 times 7 is 14. 2 times negative 3I is negative 6I. Negative 5I times 7 is negative 35I. And negative 5I times negative 3I, that one's going to be positive. 5 times 3 is 15. I times I is now I squared. See how that pops up again there. Let's combine like terms and simplify. 14, we have minus 41I. Now here, what is I squared? I squared is equal to negative 1. What's negative 1 times 15? It's a negative 15. So what you get as a final answer is 14 minus 15 is negative 1, and then minus the 41i. All right, when we look at simplifying these, just so you know, we'll come back later to, we've added, you do the same process for subtracting, you just combine like terms. We'll do division of complex numbers in the next lesson. But for now, this is how you add, subtract, combine like terms, and then how you multiply, you double distribute, and then combine like terms after that. All right, let's look at what's called the sum of squares factoring pattern. We now can do a new pattern for factoring. Just a reminder of just a little bit of review. We had the difference of squares factoring pattern. We had m squared minus n squared. We factored into m minus n, m plus n. Okay, now that's a pattern that we've been using and you've used since algebra. What happens though if you want to do m squared plus n squared and factor it? Well, what's nice about the I in what we are working with the imaginary unit, it allows us to now have an imaginary unit produce this plus in the middle. Let me show you what I'm talking about. Let's factor this. What you get is m minus ni and then m plus ni. So this is the new pattern. Let's just multiply this out to see what it looks like, just as kind of a way to demonstrate what this looks like. So let's go ahead and do the double distributive. You're going to have m times m is m squared. M times plus ni is plus m ni. Okay. Then multiply these two and you get minus m ni. Now, what happens when you multiply these two together? You get minus n times n is n squared, and I times I is I squared. These two terms get rid of each other, just like the difference of squares pattern. So you have m squared, and then negative, and you can have n squared times negative 1. I squared is equal to negative 1. Negative 1 times that gives me that positive in between those two, becomes m squared plus n squared. All right, so as an example, what if I want to do, let's bring this down just a little bit here. What if I want to do, let's factor, for instance, as an example, 25 x squared plus 64. Well, all you have to do is recognize the pattern that there's a plus with two squares. It's a binomial with two squares. And so the way to factor it is the square root of this one, 5x, square root of this one, which is an 8. And we're going to have 5x and 8. But all you need to do is make sure you add an I to these. And then you still have the minus and the plus. So 5x minus 8i and 5x plus 8i will be the factorization of this one. Let's try one more. If we have, let's do x squared minus 121, or plus 121. So when you factor it, again, you're going to have two parentheses, x and x here. We're going to have a minus and a plus. If you do the plus first, that's okay. Plus can come first. Now, the sum of these means it's going to be an 11i and a plus 11i, a minus 11i and a plus 11i for my factorization. Okay, so what we've looked at is introducing a whole new number system. The complex numbers is based on adding to the real numbers the imaginary numbers, which are the square roots of negatives. We now open up a whole new set of mathematics of how we can simplify them, which we've done the addition, subtraction, and multiplication. We'll get to the division soon. And then also it opens up different polynomials now that we can factor because of this idea that I squared is equal to negative 1. So just remember, this is a key part up here. Okay, we're going to use this a lot. The square root of -1 is equal to I, and I squared is equal to -1. We're going to come back to that over and over and over again when simplifying complex numbers.